Hello, welcome to my video on adding vectors. One of the common things you'll have to do in physics is add vectors, be that velocity or displacement or even acceleration vector. But in AP, we have to move a step beyond. So let's start really simple and then we'll scale it up. So the first thing we want to talk about is vectors that are heading in the same plane, x direction. So let's say we have this vector, which is 5 meters to the right, and we'll add on top of it this vector, which is 3 meters to the right. Now, you can look at this and you go, okay, this is 8. That's not a problem. 5 plus 3 is 8. But let's go a step further. What if we flip the order? What if we have 3 and 5? Still 8. Still adds up. Awesome. Easy peasy. So if they're going in the same direction, we can add them. That's not a problem. If they're going in opposite directions, let's see how that goes. So we have 5 right, 3 left. 5, and then because this is going in the opposite direction, we subtract it, giving us a common way to notate this is to draw the resulting vector like so. Resulting vector like so, resulting vector like so. Okay. And if we flip the order again, even though we go left 3, right 5, it still adds to 2. Okay. Easy peasy, simple math. The net result is just drawn as is. The problem comes when we're not dealing with vectors that are in the same plane, when you go over then up, or when we start moving at an angle. Today we're going to focus on things that are only moving either left, right, or up, down, and then we'll talk about combinations in another video. So let's go ahead and erase this and take a look at a slide later. So let's imagine we have two vectors, 5 meters and 3 meters again, but this time the 5 meters is going to go this way. And the 3 meters is going to go up. And now, when you're adding these, it gets a little harder, a little more complicated. Because we're not moving a straight line. This isn't 8. Vectors, or more accurately, displacement or velocity, only cares about the net result. Where do we start? We start from here. Where do we end up? Whenever you're adding vectors, the first thing you need to keep in mind is that you're always going to start from a point, doesn't matter which. The second thing is the order doesn't matter. And then finally, once you draw one vector, you connect the next vector, tip of the arrow to the tail of the next one to make your drawing. So in this case, like so. And your resultant vector goes from the tail of the first vector to the tip of the last one. So my end result will look like this. So this is the sum of these two vectors. This 5 meter plus this 3 meter gives me this blue vector overall. And again, it's not going to be 8. It's not in a straight line. It's going to be something less than 8. Well, what is it? Well, we have a triangle here. In specific, we have a right triangle. Then it's just Pythagorean theorem. A squared plus b squared equals c squared. Which in this case is 5 squared plus 3 squared equals c squared. 25 plus 9 equals c squared. C equals the square root of 34 meters. So this side over here, this blue side, is the square root of 34 meters. That's not useful. That's not practical. That doesn't tell me anything. So what I want to do is put that in my calculator and get 5.83 meters. And now we run into our second problem. Because this is a vector, we need a direction. how do we define this direction? Well, typically the way we'll handle this is we'll put it on a coordinate grid. Like so. And we'll start from 0, and we'll say this is the horizontal, this horizontal, and we'll say it's above the horizontal or below the horizontal. If we were on a different coordinate grid, we could also say this is north, east, south, west. However you respond depends on what coordinate grid you're using. If you're using the cardinal directions, north, east, south, west, this will be some amount of degrees north of east. Or we could measure from north. We'll go through and break each of those down. So the first one we want to do is we just want to find that angle. In case you've forgotten, sine, cosine, tangent is how you're going to do that. I'll typically use the numbers that were given to me, not a number I solve for, just to make sure my work's the most accurate. So in this case, it's this angle here. So we need to go through and find, using this number on this side, which is the opposite and adjacent side. So cut TOA, T, tangent, opposite, adjacent. So we need to go tan, whatever angle this is, equals 3 or 5. Or in other words, tan inverse of 3/5 equals this angle. Plug that in your calculator. Make sure you're in degrees for now. We'll talk about other modes later. 30.96 degrees. So this is 30.96 degrees. Now, reporting this is very different depending on what system you are in. If you're in a flat plane, this is the ground, this is up. We can say we're 30.96 degrees above the horizontal, horizontal being the flat line. If we're in the X, Y grid, we just say we're 30.96 degrees and moving that way. This is X, this is Y. If we are in a coordinate system, with this being north, east, southwest, we can report this as either, we can say this is 30.96 degrees north of east because we are measuring from east and then we went north from there, north of east. Or if we're just measuring degrees from the top, 0, 90, 180, 270, going around the circle, this would be 59.04 degrees. Just adds up to 90. There's many different ways you can report it. So we can even use these to discuss and describe the angle something's going.
Or the velocity it's traveling at.
A common place this comes up, or where this factors, is with airplanes. Airplanes are flying through the air. They have a speed of, say, 75 miles per hour, or faster, depending on the bigger plane. But they also have the wind to account for. And based on which way the wind's blowing,
the direction and value of their velocity changes.
Because as they fly one direction, the wind's pushing them this way, and resulting in this net result here. So, for instance, our airplane here is traveling 75 miles per hour due north. Straight up, that's north. Go ahead and put a little compass on here. There's a crosswind blowing across the plane at all times going east. Now, I say it's affecting the plane, which means it would go here, but I'm putting it up here because vectors, when I want to add them, go tip to tail. So I draw the first, and then I draw the tail, the first one, or the next one on the tip of the first. The net result is the plane ends up heading this way. How fast is the plane effectively going because of the wind, and what angle is it actually flying instead of north? So I want to know what this angle is. And I want to know what this value is. And this just comes back to geometry. But go ahead and do it on your own. Check back in after. Okay, if you did all your math right, you should get 70.60 miles per hour from your C, and 14.93 for your degrees. So how we would report this is that your actual velocity of this plane is 77.60 miles per hour at,
bearing 14.93 degrees.
which is by definition of how degrees work, east of north. And there we go.